Let us solve OpenStax University Physics Volume 1, Chapter 4, Problem 48. A projectile is launched at 75 meters per second and 60 degrees above horizontal. The base of a hill is 300 meters away, and the hill rises at 20 degrees. Unlike a standard projectile problem, the landing height is not a fixed number. The projectile lands wherever its trajectory intersects the hill. Place the shifted horizontal origin at the base of the hill. In this coordinate, the projectile starts at x0 equals negative 300 meters. The hill passes through the origin, so its equation needs no intercept. Its slope is rise over run, which equals tangent phi. Therefore, every point on the hill satisfies y equals x times tangent 20 degrees. Choosing the origin at a natural geometric point removes an unnecessary constant from the landing equation. Resolve the launch velocity using the drawn 60-degree angle. The horizontal component is 37.5 meters per second, and the initial vertical component is about 65.0 meters per second. With zero horizontal acceleration, x of t is negative 300 plus v0 x times t. Vertically, y of t is v0 y times t minus 1/2 times g times t squared. These two time equations describe the projectile, while y equals x times the tangent of 20 degrees describes the hill. At the landing instant, the projectile and the hill describe the same point. Call its coordinates xl and yl, and call the time tl. The projectile equations give xl and yl as functions of that shared time. The hill equation supplies the geometric condition yl equals xl tangent phi. The unknowns are xl, yl, and tl. Three independent equations for three unknowns confirm that the physical setup is complete before we begin the algebra. Substitute the projectile's x of t into the hill equation, then set that result equal to the projectile's y of t. After collecting terms, the landing time satisfies 4.90 t squared minus 51.3 t minus 109 equals 0. The quadratic formula gives two intersections, 12.28 seconds and negative 1.81 seconds. Both are mathematically valid for the extended curves, but only one belongs to the stated physical motion. The positive root occurs after launch and places the projectile on the actual hill, so it is physical. The negative root can also be understood geometrically. If we extend both the parabola backward in time and the hill line through the flat ground, those hypothetical extensions intersect before the projectile was launched. The algebra reports that intersection because equations do not automatically know where the real hill begins or when the real motion begins. The model's domain tells us which solution to keep. Using 12.284 seconds gives xl equal to 160.7 meters from the base of the hill. The hill equation then gives yl equal to 58.5 meters. Our shifted origin simplified the algebra, but the requested horizontal coordinate is measured from the launch point. Add back the 300-meter shift to report xl equal to 460.7 meters, with yl equal to 58.5 meters. When a projectile lands on a sloped or curved surface, the landing height is an equation rather than a number. Choose coordinates that simplify that surface. Write the projectile parametrically, and require the trajectory and surface to describe the same point at the same time. Then interpret every algebraic root using the physical domain of the motion and the surface. That strategy extends far beyond a straight hill.